Hi.
Hi, how are you?
Good.
Let's see. Um, Next midterm coming up in
2 weeks.
2 weeks. Yeah, 2 weeks, exactly 2 weeks from now, from today. Hey,
Yeah.
Camille,
Hi,
how are you?
good.
Let's see. Do you guys have any questions to start off so far?
Um,
Like
I'm
any
going
practice
through,
problem? Uh-huh.
yeah, I'm kind of behind. I'm still on your like alkynes chapter,
Oh, alkyne, right. That content review 6. I think yeah,
like
that's
three to
basically
go.
all of like
Three.
the alkene reactions plus a few extra stuff like tautomerization, eno. Let me pull that up really quick.
Yeah, I just
See.
had a question
Mhm.
on the first one and the third one.
On my content review
Yeah, like your
notes,
slides for
I
your
see.
practice.
Let me see. Mm,
Oh, and then yeah.
yeah, practice. Um, the practice of the very last page or um
I think it was like in between your notes.
in between my notes. Let's see.
Like the
Was it?
first one,
Oh, the first section of practice.
yeah, like the sodium with the excess with
So,
over NH3 liquid.
oh, I see it. Yeah, okay. Wait. This.
Like, yeah, I just got confused with what the mechanism was because, like, on the notes, it was like it went from Br2 to the alkyne.
NH3 liquid. Right. So, oh, you're thinking about the radical hydrobromation mechanism, BR mechanism. There's no bromine in this reaction here,
Yeah.
right?
Oh, was
Where,
I looking at the wrong notes?
yeah. I think you're looking at the very end of the this notes, the radical hydrobromation one.
Oh, okay, my bad.
No, it's okay. Where this is one type of reducing agent that would reduce this alkyne into the trans alkene. So that's 1, 2, 3, 4, 5, 2, 3, 4, 5. And that fifth carbon there is part of that cyclopentane ring. Carbon 2 has a methyl group. There's a double bond between carbons 3 and 4, but that double bond has to be in the trans configuration because we are using this dissolving metal reduction conditions there, right?
When would it be cis?
Yep, it would be cis if we used this reducing agent H2 Lindlar's catalyst.
Oh, okay, got you.
Mhm. Because it would stop at the cis alkene. It wouldn't overreact and go all the way down to the alkane. The thing that does overreact and goes all the way to the alkane is the regular H2 PDC, right?
Oh,
Where
okay,
from this
gotcha.
H2 PDC reaction, it first goes through the cis intermediate because we know that this reaction is a syn addition, meaning that the hydrogens attack on the same side. So we have to make them on the same side right there, which forces these R groups to be on the same side. But it doesn't stop there. It keeps reacting until it goes to this alkane right here.
Do we need to know the mechanisms
Um,
for like that, for example, sodium excess?
Sodium excess, he went over it in lecture, so it is safe to know that mechanism. But you don't need to know the mechanism for H2 Lindlar's catalyst. He did not go over that mechanism. You don't need to know the mechanism for H2 PDC as well, but he did go over this in lecture, so I would know it for the midterm.
Okay, and it's
Mhm,
on the on your slides or like in
mhm.
your notes, right?
Right. The four
Okay.
steps.
Okay.
Yeah.
I think I'm just looking at the wrong place. Okay.
Right. Mhm. Let's see. Okay. Any other questions on the practice? Like or was it all the practice problems that you
Oh no, and then I was
Huh?
just confused why it was no reaction. Is
Oh,
that
no
because
reaction.
it's not excess or anything like that?
Yeah, so when we have an alkyne like this and we react it with NaNH2 ammonia liquid, the positive charge is the Na there, the negative charge is the NH2 minus. This is our strong base right here. Strong base. This strong base will look for the most acidic hydrogen, where it can deprotonate sp carbon hydrogen, but we know that this alkyne here is internal, meaning that the alkyne is in the middle of the chain. There are no hydrogens on this carbon, no hydrogen on that carbon. So there's no acidic hydrogen for this base to deprotonate. The hydrogens on the sp3 carbons, right? All these hydrogens here are not acidic enough for this base to deprotonate, right?
Okay,
So,
so um,
yeah,
I should just remember that the NH2 goes for acidic hydrogens.
yeah, goes for acidic hydrogens such as the terminal alkyne hydrogen here. This SpCH hydrogen is acidic enough for this NH2 minus to react and give that carbon a negative charge.
Okay.
Right. Then there would be a reaction.
Okay, cool.
And then once we get this alkyne anion, that could do a whole lot of things. It could do like acid-base reaction, SN2, E2, epoxide opening in basic conditions, nucleophilic addition to carbonyl. It's that like flowchart with the 5 different arrows.
Yeah.
Yeah.
Okay. Cool.
Mhm.
Thank you.
Yeah, no problem. Let's see. Mm, see. Did you guys want to go over any other topic, concepts, any practice problems that you guys needed help with?
Could you very quickly go over the mechanism of the Na radical?
Yeah, the Na radical with like converting to the transalkene.
Yeah.
Yeah, let's do this. Let's do this reaction where we have that alkyne, converting that alkyne into the transalkene, dissolving metal reduction. There are going to be 4 steps to this. Right? Okay. So dissolving metal reduction mechanism. 4 steps. The first step is going to be the first 1 electron transfer. So it's a radical that's going to move. The second step is going to be the first protonation step, where we're going to protonate something in the acid-base reaction. The third step is basically the repeat. So the first 2 here is going to be the repeat of this. So the second 1 electron transfer. And then the last step, the fourth step, is going to be the second protonation step. Okay, so let's use this alkyne that we used in the reactant right here. That is internal, like that. The sodium radical has 1 electron right there. This sodium radical here is going to attack one of the carbons of the alkyne. So this radical here is going to attack that carbon of the alkyne. One of the bonds of the alkyne is going to move as a lone pair onto the other carbon of the alkyne right there. When that happens, we are going to get this intermediate right here, where we have a radical on that carbon and a lone pair of electrons on that carbon. Notice how this is in the trans configuration. That prefers to be in the trans configuration because it wants to have less steric hindrance. right? These R groups here are far away from each other as possible. That's why they are naturally in the trans configuration. That was the first step. The first step was the first one electron transfer. This is the one electron transfer here. Now let's do the second step. The second step is the first protonation. So once we have this negative charge here, we're gonna neutralize that by protonating it with the solvent NH3. That negative charge gets protonated like that. And that becomes what the heck? 5 membered ring, not four. There we go. Okay. Becomes this, where this carbon here gained a hydrogen, which is invisible now in neutral. That carbon there still has a radical, where the third step is to do a second one electron transfer. So that's why we need two equivalents, at least two equivalents of the sodium metal, right? The first equivalence was used here. That's the first EQ. We bring in the second EQ of the sodium metal in the third step, where this sodium metal will give that carbon another electron, making that carbon a negative charge, like that. Now, the last step here is just to neutralize that negative charge by protonating it using the solvent here, right? And that gives us this trans alkene right here that is now neutral, right? So 4 steps. The first step we did was one electron transfer with the sodium metal, and it made the other carbon of the alkyne have a negative charge, which the second step is to neutralize that by protonating it using the solvent. The third step here is another electron transfer where we bring in a second equivalence of the sodium metal to give that carbon another electron and give it a negative charge. The fourth step here is going to neutralize that negative charge by doing a protonation step. It's going to use the solvent to grab the hydrogen and make it neutral here. Right. Oh, hello, Mason. Are, how are you? Yeah. Wait, what school are you from? UC Davis or oh, you're in high school. Let's see. Wait, are you taking OChem? Oh, in high school? Oh, what the heck? Wait, how did you find about this? Oh, you found me through YouTube, not TikTok? Or did you find me through TikTok and then you went to my YouTube and then you went to here? Oh, what the okay, okay, yeah, dang, that's crazy. Because most people find me through TikTok. Yeah, yeah, I have a TikTok. Oh, dang, that's crazy. I didn't know you found me through YouTube. Yeah. It's all on my link tree, but yeah, yeah, I have a TikTok. Do you have any questions about OChem so far? Like I'm like what are you learning right now on OChem? So, okay, aldehydes and ketones. Dang. Okay. Yeah, if you have any questions on like aldehydes or ketones, feel free to like text me here on Zoom or email me the problems that you need help on, and we can go over that as well. Um, it's half semi micro crawl and half Oreo. Oh, I see. Yeah, that's interesting. Okay, yeah, no problem. Mhm. Yeah. Okay, so any other questions on alkynes, aldehydes, ketones? Any other questions?
I had a question, but it's not necessarily concept. It's
Mhm.
more like for Mascal's exams.
Yeah, my Scout's exams.
Um, so vocab, do you have
Right.
like a strategy for that? Because that was very difficult.
Oh, right. So for vocab, the best way is to like go through the textbook, read that, um, and whatever word you don't understand, right? Like look it up, try to understand it. Another way is think of it as another predicted product type of question, where you know how he likes to give nomenclature of the molecules, and it says it reacts with O3, OSO4. Draw out the whole reactant. Like if he says E2 methyl, uh let's say cyclohexene reacts with O3 followed up by a reduction step, right? Uh, The first thing I would do is draw out the structure that he gives you and treat it like a predicted product problem, where this structure here, the cyclohexene, is that six-membered ring, and we have an alkene somewhere where the one in the alkene is optional because it's in a ring. That is not optional in open linear chains. Like if it was open like this, cyclohexane, then you have to include the one right there. But since it's in a ring, that one is optional. Where let's say this is 1, 2, 3, 4, 5, 6. We also have a methyl group at carbon 2 right here. Okay, ignore the E. That doesn't make sense. Yeah, just ignore that. Right. So 2-methyl cyclohexene reacting with O3, second step, reducing agent like Me2S, right? We know that this is ozonolysis, which will cut up the double bond in half and put oxygens in the middle like that. That would give us this molecule here. This is a single bond right here. It's just a long single bond because that was the site where I cut the double bond in half, where I put oxygens in the middle. When you leave this as the product, you get full credit. But to make it neater, you could number this 1, 2, 3, 4, 5, 6, 7. Our longest chain is 7 carbons long, so we could do the first carbon is the aldehyde, so that's 1, 2, 3, 4, 5, 6, 7. And at carbon 6, we have ketone right there, right? So on vocab, he might ask you like how many carbonyls were formed, which the answer here is 2. Right? And he might give you a multiple choice, like 1, 2, 3, 4, 5, like that. The trickier vocab questions are like about more like jargon stuff, like regiochemistry, stereochemistry, selectivity, Markovnikov, anti-Markovnikov, anti-addition, syn addition. Um, in my opinion, I think Mascal's vocab is more difficult than Levin's because there's not a lot of practice on vocab for his class. But for Levin's, it's very predictable because I have a lot of like previous quizzes that are very similar to her actual quizzes. So I would just like, yeah, like know the jargon like stereo selectivity, regio selectivity, and understand what they mean for vocab. right?
Okay.
Uh-huh.
And I'll read the textbook. Like,
Yeah, and the text would help out as well. Like I was gonna say that as well, but I know like as
yeah,
if
that's
I
a
when I
lot.
was a student, I never read the textbook, so I was like I don't want to give advice that I didn't do, but that's what I would do if I had time to do.
Okay, got it.
Yeah.
Thank you.
No problem. Let's see. Any other questions? Are you a senior in high school right now, Mason? I see, I see. Are you did you get results back from college or did you apply to college? Yeah, the application process. Oh, you graduated on a Friday. Dang. Wait, so you're studying OChem early or Oh, I see. Chemical engineering. It's nice. Right. Let's I'm gonna try to do some aldehyde and ketone reactions with some alkynes. Mix the two classes together. So let's say I have this synthesis problem right here. I try to go. Yeah, yeah. Okay. So let's try this synthesis problem right here, where in the reactant we have an alkene, and in our product we have that alkene and an alcohol with an R group. Right. So let's first think about what's similar between these two molecules. We have a 1, 2, 3, 4 carbon chain right there, which I'm gonna say that that 1, 2, 3, 4 carbon chain is this 1, 2, 3, 4 carbon chain right there. Right. The new group that we added is that new R group with the alcohol right there. When you see a new carbon chain with an alcohol, think of a Grignard reagent or an alkynyl anion reacting with a carbonyl. A carbonyl meaning that there's a carbon double bond oxygen, where that carbonyl could have came from that, could have made this alcohol right here, right? So we know that this was a double bond, and we made a cis double bond here, a Z double bond. So let's go backwards in the synthesis realm. There is one reaction we know that could make cis or Z double bonds from alkynes. And that reaction is going to be H2 Lindlar's catalyst. We use this reducing agent if we want to make a cis alkene from an alkyne here, right? So now let's try to figure out how to add this group onto this alkyne right here. We know that this alkyne carbon here could be nucleophilic by having a negative charge. That means that this carbon here had to be electrophilic because this is the bond that connects the two pieces together. Nucleophile attack electrophile connect the two pieces together. That could have came from, let's say, this alkynyl anion there, a negative charge on that alkyne. That was a nucleophile. And this electrophile here could have came from this carbonyl right here, where that dotted carbon I dotted right there is this dotted carbon right here. That dotted carbon is attached to a methyl group, which is this methyl group right here, and a hydrogen, which is that hydrogen right there. When I do this reaction right here, we know that the nucleophile, the star atom, attacks the dot atom, electrophile, and it pops up the double bond to the oxygen right there, right? When that happens, we are going to get this product here. The star atom is now attached to the dot atom right there. That's the new bond that gets formed between the star and dot atom, right? Now we draw what's attached to the dot atom. The dot atom is attached to an O minus group, a methyl group, and a hydrogen. But I'm going to leave that hydrogen out as invisible, right? So that's why we need a second step of acid workup. It could be any proton source like H3O plus, H2SO4, or water. In this case, I'm using H3O plus here to neutralize the O minus by protonating it using that acid, which will give us that right there. So this is just a side note on the mechanism of how to create this structure here, right? Now, let's figure out a way how to make this alkynyl anion here. We said that the alkyne SpCH is acidic, right? We could use a strong base that could rip that proton off and make this carbon here a negative charge. The strong base that could rip that proton off is NaNH2, right? So now let's figure out a way on how to make that alkene into this alkyne right here. The way in OChem to make double bonds, one of the ways is elimination, E2 reaction, right? So let's say that that triple bond there came from this alkane with two leaving groups right here, which allows for two E2 reactions. One E2 reaction to create the double bond with one leaving group left, and then the second E2 reaction to get this whole alkyne right here, right? Where the reagents of this could be, let's say, NaOET and ethanol, right? This is the strong base right here that's going to do ET 2 times. Let's say excess. So we make sure that we do E2 multiple times. But since this is a terminal alkyne, we need at least 3 equivalents. So I'm just going to put excess to be safe. And then the second step, I need some kind of acid workup. Because after the first step, right, we are going to get this deprotonated thing right here. Oh, actually, yeah, you actually didn't need to go through this terminal alkyne. You could just go straight to this alkyne ion by using excess strong base. Because once you use the excess strong base, it will end up right here right away. So we don't have to make that neutral alkyne. Right? So then the very last thing here is just to convert this alkene structure into this vicinal dihalide here. Vicinal meaning that they are adjacent to each other. Dihalide meaning 2 halogens. To do that, we could just use Br2 and non-nucleophilic solvent, CCl4 or CL3 or something like that. Not water or alcohol though, right? So that's the whole synthesis here, where to summarize everything, the first reaction was let's say halogenation, which is bromination of alkene. The second reaction was E2 3 times to create this alkyne anion. And then this right here is a nucleophilic addition to carbonyls, a ketone or aldehyde, right? In this case, we used an aldehyde. where this nucleophile attacked that aldehyde electrophile, pops the double bond onto the oxygen to create the O- charge, which gets protonated by the acid workup to get the alcohol right there. Then the last step is reduction, specifically using H2 Linolase catalyst to convert this alkyne into the cis alkene here. Right. So this was a 1, 2, 3, 4-step synthesis. Yeah, I could talk more about nucleophilic addition. So nucleophilic addition is when we are going to add a nucleophile to an electrophile. A nucleophile is going to be any species, an atom, or a molecule that is partially negative charge or fully negative charge. They most likely have lone pairs of electrons on them as well, right? So that's a nucleophile. You could think of them as nucleus loving. Nucleus from the nucleo, phile, meaning loving. Nucleus loving, where the nucleus is filled with protons or positive charges, right? So they want positive charges. They love positive charges. The reason why is because they are negative charges and opposite charges attract. So that's the definition of a nucleophile. Let's say in aldehydes and ketones, right? Let's look at an aldehyde right here. We know that this carbonyl carbon is partially positive because it is attached to this electronegative oxygen here that is withdrawing electrons from that carbonyl carbon. That makes it an electrophile for, let's say, any nucleophile. I'm gonna give that like generic name because it could be NH2 minus, it could be Grignard reagent, it could be alkynyl anion, which we worked with, but any general nucleophile which has a negative charge is attracted to this positive charged carbon right there. Right? So this is nucleophilic addition right here, where we're going to add that nucleophile onto that carbon right there. When that happens though, we're trying to add a new bond between this carbon and this nucleophile here. That's a problem because we're going to break the octet rule. We're going to have 1, 2, 3, 4, 5 bonds. So to conserve the octet rule, we have to kick one of the double bonds onto the oxygen right there, right? That pops the double bond onto oxygen. The resulting intermediate is going to look something like this, where this dotted carbon here is now attached to the nucleophile. Before it had a double bond to the oxygen, but now it has a single bond to the oxygen. And we know that before it had 2 lone pairs of electrons, but now it has 3 lone pairs of electrons because it gained another lone pair of electrons from that bond right there, which is why this oxygen is now a negative charge, right? Where this whole process that we just did is nucleophilic addition because we added a nucleophile to that carbon right there. This is nucleophilic addition, right? And there are a lot of reactions. It's just a general term that we use to describe what the reaction step is, where this is what happens here. And once you learned about carboxylic acids and its derivatives, not like the calculus derivatives, but like the esters, amides, acyl halides, anhydrides, stuff like that, there's going to be a lot of nucleophilic addition and elimination steps as well. Right. Any other questions on this section?
Yes.
Yeah.
So on the E2 part,
Mhm.
was it NaNH2 and liquid NH3 or
This part right here.
yeah.
Yeah, so this E2 part right here, let me erase this here to make it more clear. We could go from here to here, and we could use any strong base. It could be NaOET, Or like you said, it could be NaNH2. Well, it's probably better to use NaNH2, NH3 liquid excess, right? This is the better way, the NaNH2, right? The reason why this is the better way, the better base than this one is because um once we get to this alkyne right here that has a hydrogen, right? The base that I used, the ETO minus right there, this base here is not strong enough to deprotonate that alkyne hydrogen right here, right? So this will not happen because this base is not strong enough. We need NaNH2, which NH2 minus base is strong enough. That's a stronger base, which can grab the hydrogen and go to this negative charge right here, right? So it's better to use the NaNH2. This is a weak base.
Okay.
Mhm. Yeah, yeah. Nice catch, nice catch. Right. Okay. So adding onto this right here, let's say we had a good leaving group here, like chlorine, bromine, or something like that, right? That good leaving group is still there. Once we have this thing here, this is called a tetrahedral intermediate. This means that this carbon here is bonded to four different things and a lot of electronegative atoms. This oxygen, this nucleophile, and that leaving group right there. These three things are most likely electronegative. So this is a tetrahedral intermediate that is unstable, right? If there's a good leaving group, we're gonna reform the carbonyl by using that lone pair to make the double bond between carbon and oxygen again. But that will break the octet rule. That's a problem because we're trying to make 5 bonds. It has 4 bonds right now. 1, 2, 3, 4. When we try to make that double bond right there, that's gonna have 5 bonds. To keep the octet rule, we have to kick that leaving group out. When we kick that leaving group out, we get this right here. That carbonyl with the nucleophile. And this right here is called an elimination step, where we eliminated a group, which is the leaving group there, that will leave as a negative charge, like that, right? And this is very important for the aldehyde ketone chapter, which you're learning right now. And this chapter is going to come for the last 2 chapters of 118b. And at the beginning of 118c as well. This happens like at the beginning of 118c. Right. Okay. Any other questions on this section topic, or do you guys want to try any more problems, practice problems?
More problems.
More problems? Okay, okay. Let's do more problems. Let's do alkyne problems here. Triple bonds. Let's see. I'll give you let's see, synthesis problems, and then I'll give you some time to think about it, and then let me know what you get. Okay. Let's see here. Um, let's try. Okay. This. Okay, let's try this synthesis problem here. Um, let me know what you get after you try it for a few minutes. I could give you a hint. This synthesis is gonna involve two reactions only. Wait, actually, two or three reactions, depending on what. Yeah, two or three, probably three. In the meantime, do you have any other questions, Mason? If not, you could try this as well, or just listen along and follow along.
Um, I did NH2, NH3 for uh reduction,
So
and
that's
yeah,
right. NH3 reduction, alkene right there.
yeah.
Mhm.
Oh, wait,
But how did we get this new group here?
I
Right. So back
uh,
in 19A, what reaction did you learn that makes new carbon-carbon bonds?
yeah, I used Grignard, but
Mhm.
like
Grignard, right? So let's go backwards and say that this came from this Grignard right here, right? MGBR. And let's say it attacked this haloalkane right here. Okay. Does this part make sense? Like the very last step on how I made this the Grignard, which makes this carbon the nucleophile, this carbon the electrophile, nucleophile, electrophile. Like this part makes sense?
uh yeah.
Wait, it's okay. Like if it doesn't make sense, I could explain. I could explain it from the beginning. Right? Wait.
Yeah, I mean I get it, but like I
Uh-huh.
thought it for a different way.
Oh, a different way? Like how did you do it? Like maybe yours worked. We'll try your way.
I mean, I don't know if it's right, but like I
Mhm.
used NH2 to like make it a negative alkyne.
Oh, I see, I see. NaNH2. Oh,
Yeah, and I added like a change of
yeah.
bromine of three carbons.
That's probably yeah. That's I forgot about that way. I tried to do some other reaction, but I forgot about I forgot that you could do that. That's right.
Um,
Nice. NH2, NH3, which would create a negative charge on this alkyne because it's terminal. If this
yeah,
was internal, that would not work.
yeah.
Right. So from here we could do the haloalkane, 1, 2, 3, and then that will connect 1, 2, 3 like that. And then from here, you did the Na metal excess or
Yeah.
2 EQ with NH3 liquid. Nice. Yeah, three reactions. Nice. The way that I tried to do it, right, like was probably harder, but it also works as well. You could do HBr and ROR, which is anti-Markovnikov, which adds bromine to the less substituted carbon right there. And that makes this triple bond a double bond right there. And then you do Mg to make that into a Grignard reagent. And then from here, wait, what's going on? Am I missing something? Okay. And then from here, you go to here by that as well. So this is also 3 steps, but this way is like the more common way because we don't want to deal with radicals.
Okay.
Right. Nice. Okay. See. So 118B, 118A, well, kind of 118B as well because of this nucleophile. This is what you see in 118B and 118B. Okay. Let's do some more. Let's try. Okay, I got it. Okay, let's try this synthesis problem here, where we start with this internal alkyne and we try to make these two aldehydes here.
So I did NA radical
Mm-hmm.
and
Na radical NH3, and we need at least two EQ, so we could put two EQ or
XN.
excess,
Yeah.
right? That would create a trans alkene, right? And then there's one more reaction left.
Okay. Oh, one reaction?
Yeah, one reaction.
I wrote two,
Oh, okay. What was your two? It might work. It might work.
but it might be wrong. So I wasn't sure. I added I2.
I two.
Yeah.
Oh, and
Oh,
then
is that an H or an I?
this is an H.
Oh, okay. I thought it
This
was an
is-
I.
sorry. This is an H. This is an H.
Oh, okay, so okay, then last step is O3.
Yeah.
Okay.
That's right.
Yeah, I thought it was weird with the iodine there.
Yeah. Sorry.
But would it work if it was like two iodines?
The two iodines would give us this kind of product here, where it's like Br2 or Cl2, but it will attach iodine on both carbons like that, right? And now we get this as a final product, and we can't do anything else from there.
Oh, okay.
We can't make carbonyls from there. We can't cut that because that's a single bond. Mhm.
Okay.
Yeah. Nice, nice. And Pascal's synthesis rounds, what I've seen so far based on his practice, and like real exam is like 2 steps. So this could show up on the exam, maybe.
Yeah, I think his synthesis and predictive product are easier than his vocab.
Yeah, yeah. His vocab is way harder. It's like very conceptual. Like you have to read it, understand it, and think about different angles of it. Like you have to really understand like the words that he really likes. Um, those words.
Yeah, I can't. Just go read.
I know, no. You just like seeing things, seeing pictures, drawing things, seeing patterns.
Mm-hmm.
Yeah, me too, me too. Okay, let's see. I think you are a pro at alkenes and alkynes now.
Okay.
Let's see. Want a challenge synthesis problem?
Okay.
Okay, let's do it. Okay, okay. Got it. Okay, let's try this synthesis while I'm here.
Is it racemic?
Oh, it is. Yes.
Okay.
It could be the other way as well. This alcohols could be dash or the dashes could be wedges as well. No problem, Mason. See ya.
I only got 2 steps. I don't know if that's right.
Let me know what you got. Let's see. Let's see.
I used H2PDC first.
Okay, H2PDC, and what would that create from the alkyne?
Just an alkane.
Alkane. And then what did you do after that?
I added OSO4.
Oh, so yeah, so OSO4, right?
Oh, it's only for okay, never mind.
Alkenes, right, right,
Yeah.
right. You got the last reaction, right? Like the OSO4, right?
Yeah.
Let's say that's OSO4. Second step, the something. I forgot. I'm just gonna put this. Wait. But you know how the alkene has to be right there?
Yeah, I forgot.
Right. Right. So you got this last step, right? Now we have to try to figure out how to make this alkyne at this position to the alkene here.
Yeah.
Well, first, um, let's try making this into an alkene first. To do that, we could use Na 2EQ or excess with ammonia liquid and make the alkene there, right? And you notice how this is a less stable double bond right here?
Yeah.
It can become more stable by putting H2SO4 and heat. And it will crawl to make a double bond right here. Well, you know how this double bond is now tri-substituted? 1, 2, 3.
Oh,
Yeah,
okay.
isomerization. This was di-substituted. We do
Yeah.
H2SO4 to make it like move one over to make the more stable one. And then we do it again. H2SO4, heat to crawl to the more stable position, the tetra one. So isomerization happened 2 times here.
Oh,
I know it's weird. It's weird. Think of it as like crawling to the
yeah.
more stable position. It just creeps up there.
So it goes from di to tri to tetra.
Yes, yes, that's right.
Okay.
Nice. Di to tri to tetra. Nice.
Okay.
Yeah.
I couldn't think of that. Definitely not.
Oh, right. Well, that was a weird one. I don't think he'll put it on the exam because that was really weird. Yeah. But th this makes sense though, right? Like how
Yeah.
you do
Yeah.
isomerization and then again to get to the more stable one and then the tetroxide one. Osmium tetroxide. Nice.
So like alkynes do not have H2SO4 reactions, right?
The only H2SO4 reaction for alkyne that I could think about right now is the HgSO4,
Oh, ring expansion.
H2SO4 water. Not ring expansion, um, but mercuric ion catalyzed hydration. So think of this as oxymercuration, demercuration, because we have the mercury here.
Yeah.
And back in the alkene chapter, we added alcohol to the more subside, right? So let's add an alcohol to the more subside right there. When that happens, we have this structure here. What is this thing? What does this look like?
Enol.
Eno. That doesn't stop there. It will tautomerize into the carbonyl here,
Okay.
right? So this is a reaction with H2SO4 with alkyne. It
Okay.
creates an alcohol on the more subside, and then enol tautomers to the carbonyl.
Good.
Mhm. Right. See, any other questions?
We don't need to know the mechanism for this one, right? Or yeah.
He went over it in class, so I would know
Oh,
it. Yeah.
was it a long one? I can't remember.
Uh, it is. It's okay. It's not as long as hydrogen oxidation. It's doable. It makes like a bromonium kind of ring ion, and then you break it open, on the more subside by attacking the water there, and then it forms an enol, and then you tautomerize it, and then there's a weird step where the mercury bond makes a double bond, and it makes another enol, and it tautomerize again. But
Okay.
it's doable. It's just like a tautomerization 2 times.
Okay.
Yeah. Uh-huh.
Yeah. Yeah. Thank you
Yeah.
so much.
No problem. I'll see ya.
Yeah. Bye.
Bye.